Good day. This is our lesson 8, directional derivatives and gradients. In this section, we extend the concept of a partial derivative to the more general notion of a directional derivative. We have seen that the partial derivatives of a function gives the instantaneous rate of change of that function in direction parallel to the coordinate axis. Directional derivatives allows us to compute the rates of change of a function with respect to distance in any direction. Let us have first the directional derivatives of a function of two variables. So we have here the definition. If f of xy is a function of x and y, and if vector unit or unit vector is equal to u1i plus u2j is a unit vector, then the directional derivative of f in the direction of the unit vector at the given point x sub 0, y sub 0 is denoted by the directional derivative of the function f at the point x sub 0, y sub 0 in the direction of your unit vector u is equal to the derivative of the function at x sub 0 plus su1 y sub 0 plus SU2 with respect to x evaluated at s equals 0, provided this derivative exists. The directional derivative of the function f evaluated at a given point x sub 0, y sub 0 in the direction of the unit vector u can be interpreted as the slope of the curve z is equal to f of xy in the direction of u at the given point x sub 0, y sub 0, f of x sub 0, y sub 0. Analytically, the directional derivative represents the instantaneous rate of change of f of xy with respect to distance in the direction of u at that point. For the directional derivative of function of three variables, we have here the following definition. If u equals u1i plus u2j plus u sub 3k is a unit vector, and if f of xyz is a function of xyz, then the directional derivative of f in the direction of u at the given point x sub 0, y sub 0, z sub 0 is denoted by the following notation. We interpret this as the directional derivative of the given function at x sub 0, y sub 0, z sub 0 in the direction of your unit vector u, and is defined by, we have here the derivative of f of x sub 0 plus su1, y sub 0 plus su sub 2, z sub 0 plus su sub 3 with respect to x, evaluated at s equals 0 provided this derivative exists. Let us work on this example. So we have here, let f of xy is equal to x times y, or simply xy. Find the directional derivative of the given function f at 1, 2 in the direction of the unit vector. For the unit vector u equals the square root of 3 over 2i plus 1 half j. Let us recall the formula. So we have here the directional derivative of the given function f evaluated at x sub 0, y sub 0 in the unit vector. So we have here the notation is equal to, we have the derivative of the given function evaluated at x sub 0 plus su1. Then you have y sub 0 plus su2 with respect to x evaluated at s is equal to 0. So let's find first what is this function here. So we're going to make use of the given function f of xy is equal to xy. And we now have that f of the quantity x sub 0 plus SU1, then you have y sub 0 plus SU2 is equal to, so let's now have f. What is x sub 0? X sub 0, so this is your given point, 1 and 2. So this is your x sub 0, y sub 0. So we have here now 1 plus your s is just simply s, then your u1. This is your u1. So we have the square root of 3 over 2i. Then we have yo. Yo is equal to 2 plus s times u sub 2, which is 1 half j. Oh, so we can remove I rather. So this is just now based from the formula SU2 and SU1. So this is your U1 and this is your U2. So we do not include the I and J. Then with that, let's now find your f of xy. So we have that f of xy is equal to xy. So therefore, since we have this as our corresponding equivalent of the given function f evaluated at this parametric equation, okay, so we have now that as f of quantity 1 plus, let us write first square root of 3 over 2s, then 2 plus 1 half s is equal to, this would be now your x following this given function f of xy equals xy. So this is now quantity 1 plus square root of 3 over 2s. Then 2 plus 1 half s. So if we're going to multiply these two, we have now the result, which is applying the FOIL method here. So 1 times 2 is 2, then plus the inner and the outer terms here. So when you multiply that, the result is you have quantity 1 half s, then plus this one, square root of 3s. So we can also write this as 1 over 2 plus the square root of 3. Then let's factor out s. Then when you multiply now the last terms here, so this will be equal to square root of 3 over 4s. Square root of 3 over 4s squared. And since we now have this as our unknown, we're going to find the directional derivative of the given function evaluated at 1, 2 in the direction of the unit vector. So, and this is the formula to be used. So we now have the directional derivative of the given function at 1, 2 in the direction of the unit vector is equal to, take now the derivative of this equivalent function that we have here. So you just substitute now. So this is now 2 plus 1 over 2 plus the square root of 3s plus we have this as the square root of 3 over 4s squared. And by the way, since this is a parameter s, so let's use s instead of x. So let's now take the derivative, evaluated this as s equals 0 after we evaluate. So what's now the result? We now have to take the derivative of 2 with respect to s, that is 0. The second term here, when you get a derivative, it is 1 half plus square root of 3. And then derivative of s is equal to 1. Then we have here, when you take the derivative of this third term, we have square root of 3 over 4 times the derivative of s squared is 2s. Then let's evaluate with respect at s equals 0. So simplifying now, we have the directional derivative of the given function evaluated at 1, 2. In the direction of u is equal to, so evaluate now s equals 0. So this will give us 1 over 2 plus square root of 3. Then this will be, since s equals 0, so this all be 0. So therefore, our final answer is 1 over 2 plus square root of 3.